is problems 1 through 20 of the AMC 10A. So first, this is problem 1 of the AMC 10A and also problem 1 of the AMC 12A. So what is the value of 3 plus 1 over 3 plus 1 over 3 plus 1 over 3? So this is a continued fraction, right? So we have multiple layers of a fraction. And whenever we have multiple layers like this, we always want to evaluate from the inside first. So first we evaluate this, then we'll flip it because 1 over is just a reciprocal, right? Then we add 3 more, then we put 1 over and then add 3 more. So 3 plus 1 over 3, 10 over 3, 1 over 10 over 3 gives us 3 over 10. Then we add on 3, which is 30 over 10. If we add that on, we get 33 over 10. 1 over 33 over 10 is 10 over 33. And then we add on 3, which is 99 over 33 more. And then if we combine these two, we end up with 109 over 33, which is choice D. All right. Now this is problem 2 of the AMC 10A. Mike cycled 15 laps in 57 minutes. Assuming he cycled at a constant speed throughout, approximately how many laps did he complete in the first 27 minutes? Well, first off, we can immediately tell, well, 27 is about half of 57, so we should have about half of 15. Half of 15 is around 7.5. So we can already tell that approximately it's going to be closest to 7, but we should probably do the test anyway, because we might as well do the calculation anyway, because the answer might happen to be 9, right? So let's do 15 times 27 over 57. That is 15 times 9 over 19, which is 135 over 19. And actually 19 times 7 is 133, which means that this is 7 and 2 19ths, which is of course closest to 7. So that's our answer. All right. Now this is AMC 10A number 3 and also 12A number 2. The sum of 3 numbers is 96. The first number is 6 times the third number, and the third number is 40 less than the second number. What is the absolute value of the difference between the first and second numbers? Okay, well, because the first number's value relies on the third number value and the third number's value relies on the second number value, we should just set the second number's value first. Let's call it the variable x. Well, the third number is 40 less than it, x minus 40. And the first number is 6 times the third number, which is x minus 40. And basically, the way we have all of these things being related is that the fact that their sum is 96. So if we expand this, like this is 6x minus 240, then we end up getting 8x minus 280 equals 96. So we can divide by 8 to get this. So x is equal to 47. So that gives us this value as 47, and also gives us this as 7, therefore, and therefore gives us this as 42. And we can check, yes, this meets all the stipulations of the problem, right? 47 plus 7, 54 plus 42, that gives us 96. So we know these are the right numbers, and the absolute value of the difference between the first and second numbers is just 5. Okay, now AMC 10A number 4. In some countries, automobile fuel efficiency is measured in liters per 100 kilometers, while other countries use miles per gallon. Suppose that 1 kilometer equals m miles and 1 gallon equals L liters. Which of the following gives the fuel efficiency in liters per 100 kilometers for a car that gets X miles per gallon? Okay. So what is the fuel efficiency in liters per 100 kilometers? Well, first off, right now, we're given that it's X miles per gallon. And miles goes with kilometers and gallon goes with liters. So it's actually flipped the wrong way around. So we got to flip that real quick. So if it's X miles per gallon, then that would mean that the rate is 1 over X gallons per mile. So now we can convert that to the rate we need. Well, the thing is 1 gallon equals L liters. So basically what this rate is really saying is that there are, for every 1 over X gallons, for every 1 over X gallons, we are able to go 1 mile, right? Which means that, well, if it's 1 over X gallons, we know that 1 gallon equals L liters. That means that to convert from gallons to liters, we need to multiply by L. So we multiply by L, so 1 over X times L. So 1 over X times L times G, right? So basically, this ratio becomes 1 over X times L to give us the liters per miles, right? And the thing is, we need to do the same thing for the miles. Well, 1 kilometer equals m miles, which means 1 mile is 1 over m kilometers. So basically down here, we need to multiply by 1 over m, but the thing is, it's in the denominator, right? So it's 1 over m. So this would actually cancel out and just give us this number being multiplied by m to give us lm over x, right? So let me just re-summarize that. To convert from miles to kilometers, we divide by m, but the thing is, m is in the denominator, which means m is being divided itself. So we're dividing twice, which gives us the reciprocal of the reciprocal, which gives us multiplication, right? So this m is actually being multiplied. So it's lm over x liters per kilometers now. I forgot to write this in as kilometers, my bad, but this is, oh, no, never mind, wait. This is liters per that, and now we get that this is liters per kilometers. So yeah, basically this is a very confusing rates problem, but we get lm over x, and now the final part of the problem is whether or not the 100 goes on the top or the bottom of the fraction, which is very, very trolly, because it's very easy to think, well, they added a 100 to the denominator, right? It's liters over 100 kilometers. So therefore, this is being divided by 100. But that's not true. Because they multiplied this denominator by 100, what that's really doing is that requires us to multiply the numerator by 100 to have things cancel, right? So we would actually get 100 lm over x, right? And the reason for this is simple, right? If the fuel efficiency is so many liters per a kilometer, then if we're measuring liters per 100 kilometers, that means each of those 1 kilometers gives us that amount of liters. So 100 of those kilometers would give us 100 times the amount of liters. Okay, so that is very confusing, but the answer is 100 lm over x. But what we can actually do to check our work here, right, because it's very easy to mess up on this problem, is we can try plugging in arbitrary values, right? Like, for example, what if we say m equals 2 and L equals 3 and X is 4, for example, right? And that could make it a lot easier to visualize how the problem works, right? So potentially plugging in numbers instead to check the answer here could help, right? But in this case, we're not going to check it here because this is the correct answer. Yeah, so now this is AMC 10A number 5. So we have square ABCD, and it has side length 1. And now it's saying points P, Q, R, and S each lie on the side of ABCD so that APQCRS is an equilateral convex hexagon with side length S. What is S? Okay, well, in order to make an equilateral convex hexagon, well, of course, the hexagon would probably have to have some shape like this. Like we can try drawing it, and it would probably have to have some shape like this. And of course, that would mean P is here, Q is here, R is here, and S is here, right? So we can draw it more precisely now. And we have to try to draw it so that it's equilateral. Probably like that. That's pretty much equilateral. Yeah, it's not. There we go. It's like this. That's the hexagon. And it's equilateral, which means all of these side lengths are S. And now it's just asking us to find the side length S. Well, this isn't too difficult because this is just an isosceles triangle, right? Because this is S, which means this is 1 minus S, and this is 1 minus S. So this is an isosceles right triangle, which implies that S over 1 minus S is in the ratio of root 2. And that's it. Now we can solve the problem from here because S is equal to root 2 minus S times the square root of 2, which means that S times 1 plus root 2 is equal to root 2, which means S is equal to root 2 over root 2 plus 1. And now to conjugate the denominator, we can multiply by root 2 minus 1. And that'll give us, well, this is just 2 minus 1 down here, which is 1. So the denominator goes away, and we're just left with 2 minus root 2. So that's our answer. Okay, now this is AMC 10A number 6. Which expression is equal to the absolute value of a minus 2 minus the square root of a minus 1 squared for a less than 0? Okay, so there's one thing that needs to be clarified here, which is what is the square root of a minus 1 squared? Well, it might seem like the square root of x squared is just x, right? But the thing is, that's actually not true for the case of this problem. This is not true. And the reason for this is, for example, if we plug in any positive number, right, then yeah, square root of 3 squared, that's 3, right? Square root of 4 squared, that's 4, right? Maybe like square root of 2.7 squared, that would just be 2.7, right? Square root of x squared is x, but only if x is positive. If x is negative, then this happens, right? Square root of negative 2 squared, well, negative 2 squared, that's 4, and then square root of 4 is 2. So if you notice, plugging in a negative number will also make it positive, right? So now we can realize from this that the square root of x squared is actually equal to the absolute value of x. So we can replace that into the problem. And now we see that we can easily solve the problem from here because both absolute values, when we solve them, basically because a is less than 0, we're able to determine whether or not the thing inside the absolute value is positive or negative. And actually, in both cases, it'll end up negative because in this first one, well, a minus 1, we're taking a negative number, a is negative, and subtracting more stuff. So it's obviously going to be negative. So basically, this would become negated, right? It would become negated to turn it into a positive number. So we would get 1 minus a. So we'd be subtracting 1 minus a, right? But that, when we simplify it, just gives us 2a minus 3, the absolute value of 2a minus 3. But once again, a is less than 0, so 2a is less than 0, and 2a minus 3. If we're subtracting more from a negative number, it's going to be even more negative, right? So it's not going to go into the positives. This is going to be negative, so we're going to invert this and get 3 minus 2a, which is choice A. Okay, next up, this is AMC 10A, problem 7. The least common multiple of a positive integer n and 18 is 180, and the greatest common divisor of n and 45 is 15. What is the sum of the digits of n? Okay, so let's just refresh on what LCM and GCD are again. So LCM is the smallest number that is a multiple of both of these numbers. So 180 is the smallest number that such that it is a multiple of 18 and a multiple of n. And 15 is the GCD is the reverse. It's the largest number that is a factor of both numbers. So 15 is a factor of 45 and a factor of n. So what this tells us is that n has to be a multiple of 15, but 180 has to be a multiple of n. So 180 has to be a multiple of n, which also has to be a multiple of 15. And this immediately narrows the possibilities, right? Because if we write down the multiples of 15, right? Well, the thing is, 180 is just 15 times 12, right? So n only has options of 15, 15 times 2, 15 times 3, which is 45, 15 times 4, 15 times 6, and 15 times 12, which is 180, right? These are our only options because those are all the factors of 12 multiplied by 15. But there are several problems with these numbers. One of them being that 45, 90, and 180 are all not going to work because they're multiples of 3. And actually, no, I mean, they're multiples of 9 specifically. They're multiples of 9, which isn't going to work because that'll make the GCD of n and 45, 45, right? Because 45 divides both of them in these 3 cases, right? So basically the GCD of n and 45 would be 45 in these 3 cases. So none of these would work. And furthermore, we need to have n be a multiple of 4, right? N has to be a multiple of 4 because let's say n isn't a multiple of 4. Well, then 90 would work, right? Because 180, that's a multiple of 4, right? Like, for example, in the case of 15, well, 15 and 18, their LCM would just be 90, right? And it's the same case with 30. The LCM of 30 and 18 would just give us 90, right? So these 3 also don't work. So our only answer left is 60. And the sum of the digits is just 6 plus 0, which is 6. All right, this is AMC 10A problem 8 and 12A problem 6. The data set consists of 6 not distinct positive integers. So they're not distinct. They can be the same. And also we have to keep in mind that they're positive integers. That's very important. 1, 7, 5, 2, 5, and x. The average of the 6 numbers equals a value in the data set. So the average of the 6 numbers, let's just add up these numbers and put them over 6. This is our average, and this has to equal a value in the data set. And there's only 5 possibilities for this. Either it equals 1, it equals 2, it equals 5, it equals 7, or it equals x. These are our 5 possibilities. And if we simplify this further, this sum here is equal to 20. So 20 plus x over 6 has to be one of these 5 numbers. Okay, well, let's just multiply both sides of the equation by 6. Well, then this would become 6, this would become 12, this would become 30, this would become 42, and this would become 6x. Okay, well, in the case where these are constants, all we would do to solve for x is subtract 20. So in the case of 6, for example, x would just be 6 minus 20, which is negative 14. In the case of 12, it's negative 8. In the case of 30, it's 10. In the case of 42, it's 22. And then for the case of 6x, what we would do to solve the equation is subtract x to get 5x equals 20. And then from here, we get x equals 4. So these are all the possible values of x. Except summing all these numbers, right? If we did sum up all these numbers, it would give us 14, which isn't even on the answer choices. And the reason for that is, like I said before, positive. Positive is a very key word here because these two are negative. Negative is not positive. These are not solutions. So it is just these three. So we would just add up those three, 10 plus 22 plus 4, and that would give us 36. Okay, this is AMC 10A, problem 9, and AMC 12A, problem 7. A rectangle is partitioned into 5 regions, as shown, these 5 regions. Each region is to be painted a solid color, red, orange, yellow, blue, or green, so that regions that touch are painted different colors, and colors can be used more than once. How many different colorings are possible? Okay, so this is a very simple problem if you know what order you can color these in, because, well, we can choose any order to color them in. And of course, if we count the right way, we'll get the right answer, right? So we can think about the problem in a smart way. We can think about the problem in a smart way instead of trying to count all the possibilities. Like, think about it like this. Let's say we start by coloring this region. How many ways are there to color that region? Well, 5. Let's just say that I color it red, right? There's 5 ways to do that. Okay, well, let's move on to another region, right? Well, this region is touching red, and according to what the problem says, regions that touch are painted different colors. So this can't be red. It has to be orange, yellow, green, or blue. Okay, let's say I color it blue. Well, of course, there are 4 ways to do that. Okay, let's move on to this section that's touching both the red and the blue. How many ways are there to color it? Well, that's simple. There's 3 ways to color it. But the key thing here is the fact that no matter what first 2 colors I picked, the number of ways we could color this next region has to be 3. It has to be. There's no other way, right? Because those two colors that is touching are also touching each other. So they have to be 2 different colors. So there's only 3 colors left. Okay, let's say I color it yellow. Well, let's move on to this region. How many ways are there to color that region? Well, it is touching the yellow and the blue. It's not touching the red, so it can be colored red, which means that there are, once again, 3 possibilities. Okay, let's say I color it red again. Okay, well, now let's move on to this final region. How many ways are there to color it? Well, it's touching red and yellow. And like we already mentioned, there's no way for these two to have been the same color or something, right? They have to be 2 different colors. So we only have 3 colors left out of the 5. So let's say I color it orange. Well, we know that can be done in 3 ways. All right, and now we can just use the fact of counting the multiplicity rule, which basically states that if there are like A ways to do one thing and B ways to do another things, then to do the first thing followed by the second thing is the product of them. That's how many ways, right? Because there's A ways to do the first and B ways to do the second. If they're independent events of each other, which we have shown they're independent, right? Like this having 3 colors left is independent of what we did the previous steps. We'll always have a different color here, different color here. That's what it means for things to be independent. So this number 3 here is independent of how we chose the previous colors. So this independence is what shows that the number of ways to do A followed by B is the product. And this applies to more than just 2. In this case, we're going to use it with 5 numbers, right? So basically, there's 5 ways to color the first box, 4 ways to color the second box, 3 ways to color the third box, 3 ways to color the fourth box, and 3 ways to color the fifth box. So that would give us final answer of, well, this is 20, this is 27. Our final answer will be 540.